All right, here we are back in chapter 1 now, and I'm about to define the concept of an additive function, but pretty soon, pretty much in this section, we're going to have to use the term algebra of sets rather than just sigma algebra. So let's just remind ourselves what that means. So if you have a collection of subsets of X, then it's an algebra of sets on X if and only if it contains the empty set and it's closed under intersections and, well, actually I think the way we wrote it was unions, not intersections, like this, and it's closed under complements. So these three conditions, and of course, since it's closed under binary unions, it's closed under all finite unions by induction, and since it's closed under complements, you automatically get that it's closed under all finite intersections, and also since it's closed under complements and contains the empty set, it contains the full set X. So the full story, maybe the real things to keep in mind when you have an algebra of sets is it's closed under finite everything, union and intersection, and it's closed under complements, all kinds of complements actually. So like if you do this where B and A are elements, since this can be reframed in terms of an intersection, and it contains the empty set and the full set. So that's algebra of sets. And then sigma algebra was just the version of this where I put the word countable here. Where I allow these unions to be countable, and it's still closed under that. All right, so definition 131. Let's suppose you have a collection of subsets of X. Remember, this is my notation for power set. So this is the same thing you would write as 2 to the X sometimes. So any collection of subsets of X. Then imagine that you have a function mu that assigns these subsets of X to real numbers. Then we call this function additive if and only if the following condition holds, which is whenever you have some finite collection, A1 through AN, of special sets, let's call the elements of this thing special. Usually I say measurable sets, but this is not a sigma algebra, so I wouldn't say that. So if and only if, whenever you have a finite collection of special sets, we have, and they're disjoint, then we have that the mu, which you might call measure, I don't know, but mu is not necessarily a measure here, so I'm just going to call it the mu of the union of these special sets equals the sum of the mu's. Okay, so that's additive. So it's sort of like mu distributes over union, but you need these to be disjoint. So here when I write down a list of sets and I say disjoint, I mean pairwise disjoint. So if you take any two of them, if you take any two different ones, then the intersection of those two is empty. I'm not just saying that the intersection of all of them is empty, right? Like if you have three sets that are represented by these blobs here, these would be disjoint in the sense that if you intersect all of them, that's empty. There's nothing that's in all of them. But they're not pairwise disjoint, right? So pairwise disjoint is like no two intersect each other. And actually there's a problem with the way I've written this right now. If A1 through AN are special sets, then their union need not be a special set in this setup, right? Because we didn't assume that this is an algebra of sets. We just assumed that it's a collection of subsets of X. So I actually need to fix the definition. Right now it's evaluating mu at this union, but this union need not be in the domain of mu, right? It need not be in fancy A. So it's not clear what the definition is saying. Is it saying that their union has to be in there? No, it's not actually. Here's the corrected definition. Whenever these are disjoint and their union is in there, and their union is special, then we have this. So if their union happens to not be special, then the definition says nothing about that. It requires nothing of that situation. So what if fancy A were actually an algebra of sets on X? Then I definitely would not have to say this part, right? Because it's always true that when these are in there, the union is in there. And also, if A were really an algebra of sets on X, it would be sufficient to just look at binary unions. So I can just say, just like in the definition of an algebra of sets on X, we just consider binary unions. Right? Because then, if you already know how to handle unions of 2 pairwise disjoint sets, then a union of 3 pairwise disjoint sets can be written as that, right? And then you can use the additivity on the one union, and then use the additivity on the other one. So by induction, basically, it would be enough to describe this using just 2 sets. If we're talking about an algebra of sets, something closed under finite unions. But we want to be more general than that. We want to allow this not to necessarily be closed under finite unions, hence the more complicated looking definition. All right, next definition is going to be of a countably additive function. So again, any collection of subsets of X to start with, so it doesn't have to be closed under anything. And you take a function, a real valued function on that collection of sets. So we call it countably additive rather than just additive, if and only if, well, it is what it sounds like. Whenever you have a countable collection of special sets, pairwise disjoint, with their union being special, so I need to say something analogous to this line. So whenever this is a sequence in the collection of special sets, and their union is a special set, which it might not be if this is not a sigma algebra, right? Then we have and I'm noticing that I forgot to say pairwise disjoint. The mu of the union is the sum, the infinite series of the mu's. So that's countable additivity, except I forgot to say that these have to be pairwise disjoint. So sequence, let me just do some editing here. Of disjoint sets in fancy A. So again, if we knew that this is a sigma algebra, if we knew that fancy A were a sigma algebra, then it would be sufficient to just to not include this part, right? You would just say it's countably additive if and only if whenever you take a collection of a countable collection of pairwise disjoint sets, the mu of the union is the sum of the mu's. And you would always be able to talk about the mu of the union because the union would always be one of your measurable sets. But if A is not known to be a sigma algebra, then you do not know that this will happen always. So the definition of being countably additive only considers the cases, only has you check cases where the union of your family is in the class of special sets. So why are we doing this then? Why the complicated definitions? Why not in definition 131 just let A be an algebra of sets on X, and in definition 132 let A be a sigma algebra of sets on X? Why be so general and then make things complicated? It's because our goal pretty soon is going to be to come up with sort of a general theory of how to extend functions mu from things that are not necessarily algebras of sets or sigma algebras to things that are. So because we want to develop ideas about extending mu from classes of sets, fancy A, that are more general than sigma algebras or algebras of sets, we need these definitions in order to say what it means for mu to be additive on those, well, they will end up being smaller, but on those less good classes of sets. So let me frame it this way. If we think of sigma algebras or algebras of sets as good, then our goal will be to extend additive or countably additive functions mu from non-good classes of sets to good ones. And in order to do that, we need to discuss what it means for them to be additive or countably additive on the non-good classes of sets to begin with. So another interesting thing to pay attention to is that we have an infinite series here. So immediately we are now relying heavily on our foundation in real analysis. This is partly why you cannot really start studying measure theory without already having a solid grounding in real analysis. And what about convergence? So let's suppose we have a collection of sets, fancy A, and a countably additive function, so one that satisfies this definition. What is this saying about the convergence of this series? So like, what if I take a collection and what if I take a countable collection A sub n of disjoint special sets, and it's such that their union is special, then am I guaranteed the series converges here? Yes, this is when we say this series equals this real number, that is an assertion that the series converges to that number, right? So it looks like just a little equal sign, but it is an assertion about a convergence. And the order in which you write this union doesn't really matter, right? Just set theory wise, it doesn't matter. You can rearrange a union and nothing will change. So in other words, if I'm looking at a union of a family of sets an, then that's the same as if I unioned, let me write it as sort of an ordered union, whatever that means. The notation doesn't even really allow for it. It's the same as if you thought of your ordered union, or if you re-indexed the set. Basically, the indexing doesn't matter. So if you thought of it like this, let's say, apply a permutation to the indices, where sigma is a bijection from n to n. So permute the indices in any way, it's not going to change the union, right? In fact, the union doesn't even care how you indexed things. It's just taking the union when you write this. Unlike a series, it's actually just taking. It's pretty much this. So it's if you look at this, it doesn't care about any ordering you placed on the index set, right? The index set does not have to have an ordering. It's just this is the only place in the definition where the index set gets used. no ordering structure is needed. So this is sort of even silly to write, I feel. Yeah, so you can re-index and nothing will change with this. Therefore, if you have a countably additive function and a sequence of disjoint sets like this, with the union being special, then this is not only saying that the series converges to this number, but it's saying that the series converges to this number regardless of how you rearrange the terms of the series, which is not something that is true for all series, right? What kind of series have this feature that you can rearrange the terms however you want and they will still converge? What kind of convergent series have this feature? So here I am back in our text from 118a and part of B, the text by Abbott. This is the section 2.7 on series, where we discussed rearrangements. And we worked pretty hard to prove this one direction of things, which is that if a series converges absolutely, then any rearrangement converges to the same limit. And this was pretty cool, kind of notationally annoying, I remember when we were doing this. But there's a part that we didn't quite cover, which is down here in the epilogue. So one thing that's discussed here here it is if you have a series which converges conditionally, not absolutely, then here it is. If your series converges conditionally, not absolutely, then for any real number, there exists a rearrangement that makes your series converge to that number. And then he shows you a suggestion for how to show this using the harmonic series. So then this tells us, in this context, since we know that rearrangements will not affect the value of this series, the series must converge absolutely. If it converged conditionally, then there would exist rearrangements that change the outcome. You see this left-hand side does not change to rearrangements. So in summary, when you say that a function mu is countably additive, you are asserting that a bunch of series converge, and you're actually asserting that they converge absolutely. All right, and one final quick thing. If you have mu additive or countably additive implies additive, right? If you have mu countably additive, and suppose you're in a situation where the empty set is one of the special sets. It would definitely be if you were looking at an algebra of sets or sigma algebra. Let's assume the empty set is one of the special sets, and mu is an additive or countably additive function. Then can you prove that mu of the empty set is 0? So this is one of these fun things. Maybe you can pause the video and try it. And here's my suggestion for how to do it. This is a very common standard trick if you've taken an algebra class, basically, or even just linear algebra. So notice that the empty set is the union of the empty set with itself, and the empty set is disjoint from itself, right? The intersection of the empty set with the empty set is empty. So according to additivity or countable additivity, you have this. Then look at this overall equation. You can subtract mu of the empty set from both sides, and you get mu of the empty set equals 0. Yeah, so this is something you see in a trick seen in algebra all the time. You can think of it as sort of saying that since mu is additive, it's almost a homomorphism-like property, right? Mu of a union equals the sum of the mu's, except the operation you have on one side is union, the operation you have on the other side is addition. So if fancy A is an algebra of sets, then you can think of it as not a group, but I guess a monoid with respect to the union operation. And then to say that mu is additive is partly saying that mu is a monoid homomorphism, except not really, right? Because it requires that you be looking at disjoint sets. But anyway, just like in algebra when you're looking at homomorphisms, the identity element is sort of preserved, or the idempotence of an element is preserved. So the empty set is idempotent, so its image will have to be idempotent, and the only idempotent real number is under addition is 0. All right, so as you might guess from the definitions, even though countably additive just seems to add a little bit more to what additive is saying, it's just saying, now let's define something where it works for countable collections of sets rather than just finite. It looks minor, but countably additive is actually a lot more complicated, right? So let me put it this way. No calculus up here, just set theory basically, right, and arithmetic. Down here, calculus. You've got an infinite series. This is real analysis. So our next theorem in the next video is going to be looking at ways of, alternative ways of describing countably additive, because the way it's set up right now is not always the most convenient way to use it.